Okay, so the last part of this, as I was just saying in the previous video, so when we have a surface defined as z equals some function of x and y, using our generic formula to get the surface area with our parametric functions, we see that we get our surface area double integral that we had used at the end of chapter 15. So this is just another case of a common theme we keep seeing where we've already encountered something that is really just a special case, and now we're trying to get more general. And I mean, that's generally what you do in upper level mathematics, is you start taking away our specific ideas of math that we've been working on for years and years and years and try to make them as general as possible. So the concepts and ideas we've encountered in these past two sections, which were curl and divergence, and then for 16.6 is our parametric, not equations, surfaces, and their areas. That's going to be the building blocks for the rest of our chapter. In case you wanted to re-look at this, I'm going to do a problem similar to something we did in 15.5, just so we can practice using the formula. So we're going to find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So our set that we're integrating over for our xy's is such that x squared plus y squared is going to be less than or equal to 9. If you think about our paraboloid, when we project that down into the xy plane, that is going to give us this circle right here is going to project its shadow right there, which is our circle of radius 3, so we'll be needing to integrate over everything inside of it. So our surface area will be given by the double integral over d of 1 plus del f del x squared plus del f del y squared dA. So looking right here for our partial derivatives, that is, I don't want to write A again. That is going to give us our double integral over d of 1 plus 2x quantity squared plus 2y quantity squared dA, which is equal to double integral over d of 1 plus, I'll factor out a 4 out of here, so x squared plus y squared. You might be thinking to yourself, how is the best way to approach this double integral? I'm hoping you're thinking along with me that polar is the way to go. So we're going to integrate from 0 to 2 pi and 0 to 3 of what would be 1 plus 4r squared underneath the radical, but because we're going to polar, we need that factor, conversion factor, so don't forget your r, and dr d theta. That allows us to actually do this integral without needing trig sub. Because this function just has r's in it, we can actually split up this double integral because our bounds are constants. So we can do the integral from 0 to 2 pi d theta, which just equals 2 pi, times integral from 0 to 3 of r square root of 1 plus 4r squared dr. Looks like our substitution factor is going to be 1/8 if you let u equal 1 plus 4r squared. So it's going to be 2 pi times 1/8 as our substitution factor. Now we are integrating the square root, so that is going to be something to the 3/2, which means we need a 2/3 out front. That's going to be 1 plus 4r squared to the 3/2, and we need to evaluate that at 3 and at 0. Please don't get lazy. Plugging in both of those does yield a number. Simplifying all the constants out front here, it looks like we are going to get pi over 6, looks like. And then we plug in 3. That is 37 to the 3/2, so maybe I'll write that as 37 root 37. We plug in 0, that's 1 to the 3/2, so minus 1. There is our surface area. Okay, that is the end of 16.6.2. We will be digging in way deeper into how this stuff will be used to find some other types of integrals over vector fields. So we're going back to this idea of we had line integrals over vector fields, and now we're going to be doing surface integrals over vector fields and talking about what that stuff is. So that's coming up next week after our quiz. Hope this is beneficial to anybody that has chosen, not chosen isn't a word, chosen to watch this.